Welcome. I am Max Seeley. I am from 3M.
I'm Carl Schattke. I'm from a company that's an EV company up in Silicon Valley. We're very experienced, both of us. Max is an electrical engineer. I'm primarily a PCB designer. And what we want to cover today is how we go from schematic to PCB and how to do that in a way that is highly effective.
And I would say, coming into this presentation, one of the things that we wanted to discuss is Carl and I kind of exist in two different paradigms. So I'm an electrical engineer that's doing, everything from the design capture to the PCB layout, where Carl is primarily operating in a space where he is getting designs handed off to him from electrical engineers and having to deal with that transition. And I think coming into this, I was expecting to see a lot of differences in the way that we approached how we did things. And I'd say the thing that really became apparent the more and more we talked was that our methodologies and approaches to that process, and especially that transition, were almost identical. I don't know if we disagreed on anything, and I don't know if we found any key differences.
One thing is each of us works in a different environment and designs for different needs.
Yeah.
So there's lots of different types of designs. Everybody in this room works for a company that has a unique product. And what's effective at one company or for one design might not be effective. So we had to choose a track, and today the track we chose was high volume and high reliability. So each project that you start has these four aspects to it: scope, schedule, cost, and quality. So each of those can be a high priority. Whenever we start a project, understanding the scope of it is extremely important for the design that we do. Where is this design going to be used? What are the conditions physically that it's going to be under? What are the temperature, vibration, thermal constraints that this project's going to have? So we need to know that. What size do we need to design it into? What are the advantages if we make it smaller? What if it has to be lighter? So this scope drives everything else. And we also want to find out if that scope's going to migrate. Like what are the risks of scope creep during the project as well. As PCB designers, I'm sure we've all been handed changes through the process, right? That's kind of what we see. The schedule, if we need to get it done as fast as possible, there's a big difference between doing a motherboard in 4 layers or using 12 layers. You can design a 12-layer board much faster than a 4-layer board, but economically, if cost is your consideration, you'd much rather have a 4-layer board and be able to sell that product for significantly less into the marketplace. But if it's first to the marketplace for the advantage, then you're going to look at that schedule as the primary mover. Like, let's get this thing done and out the door as quickly as possible. Let's have our product before anybody else does. This is a new part that's come on board. You want to take advantage of those things really quickly. That's going to be your driver. If it's cost, it might take a little longer to design, but you come in at a lower cost. Now you have an advantage in the marketplace that way. Quality is another aspect to this that I put quality and reliability in the same terms, but the quality of your product is as a designer, we want 100% quality all the time, but quality means different things to different people. And reliability, number one, but how long does that product have to last? If I design a cell phone, I was told they only last like 2 years, and most are changed after 6 months. That's a lot different than designing something that has to last in space, for instance. If you're sending a satellite up, the Hubble telescope's been up there a long time. Their primary mission was to have high reliability. And then also, the quantity of how many you're building is going to have a big impact on what types of efforts you take. So these are the 4 levers that we get to move as PCB designers and engineers to more effectively plan out what we're going to do and the approach we take and how we go through our schematic and PCB process.
Yeah, one thing I would say is one of the common things that I think that we, depending on the schedule, what I see a lot, and I'm a firm advocate of resisting this, but if there's a really tight schedule, what I see a lot of engineers do is cut corners in the process, thinking that they can get something to the fab shop faster, and when you're dealing with a board that has a 21-day turn time just for fab, and you've got a mistake that you can't fix, then that extra time you got by cutting corners will definitely come back to bite you. So in this presentation, we're going to cover 4 main topics. So we're going to talk about methodologies in schematics and best practices in schematics and some of the tools that exist in schematics that then translate to the PCB. We're going to talk about pre-layout simulation and some of the simulation that you can do prior to laying out a single trace on the board that will give you higher confidence and better results in your PCB layout. Important discussions that you need to have. I mean, this isn't just, if I'm an electrical engineer, it isn't just the conversation that I'm having with my fab guy if I am passing it off to my fab guy for that portion of the project, but these are important discussions that need to happen on any project and definitely need to include the fab guy, whether the fab guy is a dedicated fab person or designer, or if the person doing the design is the electrical engineer. And then the last thing we're going to talk about is setting up the PCB layout or setting up the PCB for layout. So all the tasks that you should be doing prior to laying down a single trace on your printed circuit board and not doing these things on the fly. You have anything you want to add to that?
No, I think that's great.
Okay.
We have a lot of material to go through, so we're going to get right into it.
Yep. So some of this, I've given a presentation here on schematics, and so some of this, this first section is going to pull a lot of that presentation in, but there's some stuff we added. And one of the things that I am a huge advocate of is hierarchical design. And furthermore, I'm a huge advocate of hierarchical design with color codes for your top-level sheets. And the reason that I am an advocate for hierarchical design, there's numerous reasons, but what this top-level schematic does for me is it allows me to see the organization of my design. So I get to see how the functional blocks are connected, and furthermore, by color coding it, I get to see, this is really going to lend itself to how I organize my PCB. So, prior to coming down here, there was a project that I was going to do layout on, and I had to pass it off to an engineer on my team to do the layout. And he was asking me, how do I want to organize the design? And by pulling this top-level schematic up, I was able to, in 5 minutes, show him exactly how I wanted the different structures organized on the board. One of the other things that I want to highlight on here, and you'll see as we kind of go through some of these additional slides here, is kind of the methodology behind my color coding. So I call out connectors, and I can't emphasize this enough. And this is actually one of the areas that I get the most pushback from more traditional electrical engineers. They get really pissed that I devote an entire schematic page just to a connector. And all of the stuff associated with a connector, they think it's a huge waste of I don't know, digital real estate. I guess when you print it out, you're wasting a piece of paper, but I think we'll live. But what it allows me to do is, my connectors are one of my absolute focal points in my design. Are they protected via ESD? Are they positioned correctly? Have I done all the things I need to deal with EMI on those connectors? Same thing with power delivery. Those are essential elements in my design. I don't think I need to go into further explanation on that.
In my experience, connector protection, ESD protection, is one of the most neglected or forgotten areas in PCB design. It's definitely one of the most commonly like a lot of mistakes for second pass design are at this point. So, by putting a lot of emphasis on that with a separate page for the connector, it really helps Max ensure that he's got good, adequate ESD protection and EMI protection for those connectors. And in my experience, that's where most rework is right at that connector. And if they've pushed all the parts right next to the connector, it's one of the most painful too, because now you have to move everything to make room for the ESD components that need to be near that connector.
Yeah, I mean, I've did this at one point in my career, and I've seen tons of engineers do it. They do their entire design, they go through prototyping, they verify functionality of the circuit, and then they think, oh, shoot. That wasn't the word I was going to use. They think, I got to do certain things to pass, my regulatory compliance, and I'm just going to, throw in these TVS diodes at the end, and it's an absolute recipe for disaster. So, yeah, this really lends itself, and let me talk about the other critical things that I'm looking at here. I mean, as I go into my PCB layout, so I'm placing my connectors almost first. The other thing that I'm easily identifying in here are my critical buses. So what are my high-speed buses, and how are those connected in the design? I would be interested at the end, I don't want to get too off track here, but I would be interested in the end from hearing from someone about how they do this effectively in a flat design. Because for me, and maybe I'm just not seeing it, maybe it's more difficult for me, but I really have a challenge doing that in a flat design and seeing that how things are structured. And lastly, I have my antennas on a separate schematic as well, and identified and called out in the top level. Also, don't forget fiducials and tooling holes. I think that's important to have represented in the schematics as well.
Yeah, and sometimes the PCB part number can be listed on your schematic so that when the BOM's created, they have a part number for the board to order.
Sure. Do we want to intermix the demo or just do it at the end? What are you leaning towards? Yeah, that's what I'm kind of leaning towards as we get going. Harnesses. So I am a huge fan of harnesses. Can I see a show of hand of how many people use harnesses in their design? Okay.
About a third.
Yeah. So the thing I really like about harnesses is that, I was just showing the previous schematic and showing how the design itself is organized. What harnesses show me, and you can get this by net naming, but to me it's much more clear with the harness, and what it shows me is how are my signals organized? What signals go together? What are signals, that I have to maintain timing constraints between, and it allows me to see that. And what Vince is going to show at the end is some really cool tools and tricks with harnesses, and what harnesses aren't as difficult to set up as you think, and once you do set them up, they actually make things a little bit easier, and we'll show that in the demo. Any?
Yeah, let's move on.
Okay. It's funny. One of the cool things about teaching is it's the best way to learn. And I forgot about this. I forgot, if you look here, I have, each of my individual data lines called out. And I forgot that I could also do a bus and a harness, and I was looking at one of the old Altium reference designs for some of the nanoboard stuff, and then I remembered that you can actually include a bus in the harness itself. So now I've shrunk my harness size down tremendously. Now you want to see some, I mean, a lot of the stuff that I'm talking about was really present in some of the early, I don't know if everybody in this room knows this, but Altium used to make quite a bit of hardware. And some of the best practices I've seen are in the design files for that hardware, which are readily available on Altium's website, or I think in the vault, maybe. Carl, you want to talk to this? I mean, functional blocks.
So with functional blocks, when we organize that schematic, we want parts that are of a similar function to be co-located. That way when we import into the PCB, we have a room for that schematic page. And then this also lets the designer know that these parts that are in this functional block need to be placed closely. Here we have some termination and some capacitance that's local to this. As we examine each page as a designer, we're looking for things that are the highest priority to place. And if I'm working with the engineers, I review the schematics, I would ask Max, like, is the placement of L1 critical? And he's going to let me know. Does that need to be close by, or is it okay a little bit farther away? Obviously, like the diodes probably don't need to be close. But I'm going to be asking him those kinds of questions. And if you arrange your schematic in functional blocks, when you import it, then you're not mixing different functional blocks. And when you search for a room or work on that room, you can just hit the room and then hit TOL and bring all those parts in one spot and then move. And you're right on, like they're all co-located, and you can just start, with the placement of that particular block. And what I find as a designer works best, I'm probably getting a little bit ahead, but is to co-locate those parts first into groups. We're going to talk placement strategy later. I think let's save that for later.
Yeah, and just a couple of quick points I'd make on this, and this is what I really like about functional blocks is it takes one data sheet to review the schematic. So I just have to, the engineer reviewing the schematic just has to open up the data sheet for this part. The other thing that I've done, I can't tell you how many times I have opened a design that someone else has done at my company. And I have no idea why they made certain decisions. And I will go into data sheets, and eventually with some hunting, I will figure out why those decisions were made. Sometimes I can't figure them out, and that's really frustrating to me. So if you're doing something in a circuit that's odd, that's because of a unique behavior with the IC. We had one IC where we had to put a diode on one pin, and it was because of a defect with the silicon. And we were struggling with this, and we called up the IC manufacturer. This is a little bit of a side story, but we called up the IC manufacturer. I won't name who it was, and we were really struggling with this. And then about a week later, the FAE, sent me an email and said, "Oh, we solved this, and here we've got this report, on how we solved it." And I was like, "Wow, this is awesome! It's like a 5-page report. They've really done their work." And then I noticed at the bottom of the report, it was from like 3 years ago. And I called up my FAE and I said, what gives? Why are you doing this? What happened? He said, well, we figured out that problem a long time ago, but we didn't want to put it in the data sheet because we didn't want to give one of our competitors an advantage over us in terms of component count needed to implement this device. So anyways, side story, that would be a great thing to put a note in my schematic about. So the next engineer understands why that weird diode is on that one pin. But the other thing I would say about notes and schematics is that they help me. So as I'm going through prototyping and I need to make adjustment to some of the things that are flexible in my circuit, whether it's for this one, this is a gas gauge, and I've got resistors on here it's a charge management IC. I've got resistors on here that set certain current limits. Well, every time I need to change one of those, I can open this part, open the data sheet, or I can take 10 seconds and copy in the table that is the basis for setting those components. Sorry, kind of a tangent there. I'm talking too much. All right, design notes. I think we just talked about this. This is Robert. I took this off of one of his reference designs, and we've started using it in my company, and we just love this. And I think this really breaks down the really pertinent notes that you should be including in your schematic. So I think these are pretty self-explanatory.
Yeah, that's definitely a best practice, is to color code the notes for the individual that's going to need it. If I'm a designer, I'm going to really pay close attention to the blue notes. If I'm, a debug engineer, I'm going to look at those, orange ones up above.
Yeah.
So it's very helpful to, have that on there.
Power delivery map. So how is your power delivered across your PCB, and what are the steps to do it? And this takes some time. And this is one of those schematics where, I would admit that now we made this in Visio and then just imported it into our design. This is one of those schematics if you are, rushed to get something out the door. But, you can see how many steps the power delivery network takes in this design before it gets to a certain component. And so this really makes it clear the structure of that power delivery network.
Yeah, so as a designer, when I'm looking at this, I see that there's, a charging system, and then that's followed by a PIMIC, which is going to be very precisely laid out. If you look at most data sheets for those, they're extremely long, and there's almost always something on the PCB layout because it's super critical. Usually that PIMIC is going to have all the power that it's generating, but it's also going to have the sensing for that, and it's also going to have, that's a very critical aspect to controlling the noise on your PCB. And then once we get out of that, then we see maybe some voltage dividers, or that's creating the different nets that are going to get to the components and the component functional blocks, near that CPU. So, that PIMIC is going to be a super critical part of the layout.
One thing I would say about power delivery and something that I do, you've got EMI issues to consider, and switching power supplies usually end up being big contributors to noise on a circuit board. But what I would say is for me, and I'm interested to get your feedback on this, is if I've got 20 watts coming into a board at 20 volts, and then I've got power conversion that steps that down, what that means is if power is conserved, except where it's lost in the power conversion, but what that means is when I step down to a lower voltage, my current is going up. And so what I try to do, and when I'm looking at this, is I try and locate my power conversion devices close to the devices that they're supplying. And sometimes we go the other way, though, where we'll try and consolidate the power conversion on a board to one section of the board. But generally I've found it advantageous to include, to bring the power conversion closest to the devices it's supplying.
Yeah, in the placement, I'm typically going to try and co-locate parts with similar power. If I can co-locate those, then I'm hopeful that I can do a split plane where I'm going to be able to break these things out in a way that's going to fan out that power to different areas of the board. So I can do a lot of twists and turns on that split power plane, but I'm really looking to use as few layers for that as possible. In modern embedded systems, it's all about power management, and sometimes these boards will get dozens or up to 100 different nets, and it's super critical to place the components in a way that you'll be able to supply power to them.
So really quickly, this is an extension of that table, but basically what this table is showing me, and I do this in Excel, it's showing me, how much current or how much am I utilizing the capability of a certain rail. And one of the things that we were talking about prior to this is this, tells you if your trace or your pour is thick enough to support that current delivery. But I think also from a layout perspective, we're not just looking for thick enough. A lot of times in design optimization, we are looking for how thin can we make it. How much can we reduce that before we get into trouble. And what I see a lot is engineers get really lazy about this. And they say, well, I've got a switcher that can supply 5 amps, and so I'm going to design that power delivery network to handle 5 amps. And if you got the board space, why not? But sometimes if you've got a switching regulator that's capable of delivering 5 amps and you're only using an amp on there, then size your power delivery network in accordance with that requirement. I don't think we need to talk too much about this. This is one of my schematic pages devoted to a connector, but you can see that I have all of my filtering required for that specific connector, and in this case it's a USB connector, all the ESD on that schematic, and we talked about the reasons why I'm a fan of that. Carl?
So with using a harness for a high pin device, what's nice about this is if we don't directly connect these, when we get to the board and we want to do pin swapping, we can take advantage of the pin swapping in the tool. If you directly connect these harnesses, you avoid the opportunity to do pin swapping, even if you have your part enabled for pin swapping. So it's critical not to go right from your part to the net label and leave it at that. You want to have that separated.
And that's really going to save you some time on high pin count devices. Not only does it allow, from an electrical perspective, from an electrical engineer's perspective, allow me to make changes if I remux a pin for a different function. But when we're laying out the PCB and I'm backed into a corner and I see that 5 pins that are more on that side of the IC are open, now I can readily change assuming it's allowed by the function of that pin. Now there's at least a path to changing to a pin that's easier.
Yeah, it definitely greatly simplifies the escapes. Yes?
Since I'm like you, just doing the layout and engineer that, even if hardwired stuff is not swappable, they'll leave all the stuff that's swappable broken. So I didn't have to go ask them, hey,
That's a great practice, yeah.
Yeah, that's a good tip.
same practice, but just one step further.
Yeah, no, I like that. That's a great idea.
So how many people here are rigorous about clearing out all their ERC warnings and errors? Okay.
All right, so we have a lot of risk takers in the room.
Yeah.
So this is a really good idea to view them for sure. I would say if it's an error, that should be resolved. And if it's a warning, it should definitely be looked at. And the risk is that, you know, on a large schematic, you might have several thousand of these, and it takes time to go through it. But the biggest risk is that if a real error comes up, or you'll miss it. So you want to try and whittle this down and get a clean schematic compile so that you're not, you know, having errors for a great number of entities in that.
And so I'm actually pretty anal about clearing all of these out. And one of the tools that exists is the specific ERC suppression in Altium, which I will go through and I will, you know, suppress all the ones that are okay. And I have found mistakes every time I've done this. So I agree with Carl, clearing out the errors is a must. But I have found things that need to be fixed in the warnings and have saved me some headache once I've gone to fab. So just real quick, and you know, we won't, I think people should be familiar with how these are set up in the project options. I think a lot of people just go with the default, and these are really, the ERC errors are really driven from two tabs in the project options. One is the error reporting, you know, which we don't need to go into details, but when you get back, open this up and look at it and see if you understand it. And if there's ones in there that you don't understand, you know, just spend a little time and figure out what they mean.
There's one default that's kind of a gotcha in this area, and that's for single node pins. It's put in there as it's not going to report, and like usually you want to know your single node pins, because if you gave it a label, it should probably go to something else. You know, otherwise you wouldn't have bothered to label it.
Yeah. Yeah, most of the time for me, a single, you know, single node net is the result of me screwing up a net label. Connection matrix. So again, same thing I would say with the previous one. Understand this, and it's fairly, you know, self-explanatory. Here's what a lot of people do. They ignore this because they have set up their schematic symbols entirely with passive pins. And so then you don't really derive any value from this. I'll just say that there are some tools, the schematic symbol wizard, and some other tools for copying schematic symbols or setting up schematic symbols from, you know, Excel sheets that really enable you to do this quickly. And I find that it's not that much more work to set up the electrical type of a pin on my schematic. And again, it's something that has saved me. No, and I think some of the pins, some of the electrical types, it's obviously a feature that has not gotten a lot of attention recently and isn't comprehensive for sure. So parameter sets.
So one of the big errors that I see with this is people will name the parameter and the name won't be what the class, they think that the class name, you know, like they name the parameter and think they're done, but actually it's the blue part that matters. The red part is a story. The blue part is the action. That's the most common mistake I see with parameter sets.
And do people, so right here, this does not give you the class name, okay? So to get the class name, you have to set it up down here. And the other thing that you can do is you can put, when you create a parameter set to create a class in your schematic, and you know, in complex designs, classes are really the basis of the majority of your rules.
Yeah, our rule hierarchy is definitely driven from the class names. And as you notice in that lower example, there's two classes. So a net can be a part of different classes. They don't have to be in the same class.
But this can allow me to set up a hierarchy on my net names, or I mean, sorry, my classes. So, I've got certain timing requirements that apply to the entire data bus, and for instance with DDR, including the strobe. So I can set that up into my DQ class, and then I can put that into the bigger class for the entire bus itself. And that'll help with rule generation.
So, this is an example of how to set up net classes with a blanket. So we see drawn around the action point, in a net label is the lower left corner. So we have two blankets here. On the top is DRAM bank 0, and on the bottom is DRAM bank 1. And all of the nets that are in that box are going to be in that. You can also just loosely, you don't need the wires in order to have the class. You just need the net name. So we show it here with the class. The other thing that you can do is put at the end of the wire, if the blanket encompasses that, then it's going to also pick up that net.
So one thing I'll say that has caused me problems in the past is the hot point for the net name is, I think it's a little dot at the lower left-hand corner of the net name. And I've had problems when this is right on this line. That last net does not get included into the net class. So you got to bring this down one more space.
Yeah, so it's a good practice to have adequate space between your entities on your schematic.
Yeah. So here we're going to set up, and you can talk about this a little bit, and then I just got one point I want to make about it.
So obviously _P_N, that's going to be denoting a differential pair, and that's how across all Altium, that's how it likes to see it. You can set that up differently in the PCB, but why would you? The schematic should be driving this, and then we put that differential pair directive on it, and then it comes in as a differential pair class based on that.
So you have to do.
Sorry, thanks to a feature specified, you can now drive it to their class now.
Yes.
Right. Yeah, we definitely want to do that. And if you've created your stack up, you can import the stack up into the schematics now in version 19 and forward. And if you've also put in your differential pairs or into the stack up, now you can call those out here. And it greatly simplifies the rule writing, and it carries that forward.
The only thing I'd say about this is, and I got an explanation from someone at Altium. It always kind of bugged me that we had to do both. I had to do the _P and the _N and do a differential pair directive. And that was really a relic of, the explanation I got was that was really a relic of pleasing users that might have had these designations for certain pairs on their schematic, but didn't necessarily want to bring them in as a differential pair into the PCB. And so that's why you have to do both. Use the _P, and so we're a hard group to please, I think, is the message I heard there. The other thing I'd say is, this is a small thing, but I see a lot of people name nets with using underscores, and I have to use underscore for a differential pair. But in general, one of our rules is in net names, we always use hyphens. We never use underscores. We've had issues where, if this were underscore, we've had one net named, using the underscore and one net named without it. and it gets obscured in the wire in the schematic, and so you don't readily pick that up.
Yeah, spaces in net names are really bad. What Altium will do is if the prefix is the same, it's going to ignore the suffix if you have a space in your net name. So as a general practice, it's a really bad idea to have spaces in any net names. So here we have a rule. It's you're putting it in as a property for a width constraint on your design, and these are super helpful for the designer. This particular rule, as it's set up here, is wrong because the preferred width is 100, the min width is 100, and the max width is 10. So this one would be an error, but. Generally we'd like to have a range as board designers. This would be like, hey, Max, you might want to change that rule. Like, I would definitely send out an email on something like this. I'm sure this rule was put in late at night, and this is what happened. So, but that's like what we're looking for, is to review the rules and put them in the common sense meter and see if anything, triggers. And so unary rules are rules that apply to one entity. Binary rules are one thing against another. So all the unary rules typically can be put into the schematic. If it's like, we're going to put this on a net, and it's going to say, hey, that has to be 10 to 100. But if we want to have a clearance rule, that's one entity to another entity. Those are going to be your binary design rules, and those are typically placed into the design at the PCB stage. So that's the primary difference between your unary rules and your binary rules, is where you enter that rule into your project. So obviously, the more you put into the schematic, the less you're relying on the board designer to pick up, and put in during the PCB start phase. Okay, so when we generate rooms, we get the classes based on the sheet name, and then we generate the classes and the rooms, and this is why I was saying earlier, this is super helpful in the beginning. Maybe after you're done with the placement, you turn this off and update it, and you don't need the rooms once you've done the placement. But typically, this would be a normal way to set things up. For your generating component classes and net classes, and then that's going to allow you to have every page have its own room, and then when they import in from the schematic, you'll have those boxes with all the components, and they'll be pertinent to each other based on the schematic page. And that's why you want to functional block your schematics with, don't put a USB circuit with your Ethernet circuit. They're two different functions. Put your Ethernet on one, put your USB on another, bring in 2 pages. They don't charge for extra pages.
Yeah, and I would say that if you don't have those functional blocks set up, then you have to partition your design once you import in the PCB if you really want to take full advantage of component classes. And by having a component class set up, I can then go into the PCB panel in the PCB and readily see exactly where all of those components are on my PCB by selecting that component class. The other thing that I learned, and I did not know this, I'm going to be using this a lot, is you saw that I love to use harnesses, and that I've been using, in addition to that, blankets to name my classes. But if I did a good job of setting up my harnesses, and I literally learned about this option yesterday. If I do a good job of setting up my harnesses, then my harnesses can create all of my net classes for me, and I wouldn't even need to do blankets. So I thought that was pretty cool. Yeah, and again, kind of back to the error reporting and the connection matrix. understand the options, and I just proved that I am guilty of not understanding all the options on this, and it's coming back to haunt me.
Altium's a really complex tool. There's thousands and thousands of functions in the tool. So, you know, even though I've been using the tool since the mid-'80s and new things get added all the time, there's nobody that works with the tool that doesn't learn something new all the time. Like, you know, I'm sure all of us saw something here coming to AltiumLive that we're like, oh, I didn't know you could do that. Like, I got that. And, you know, like, that's what's great about events like this is, you know, you're able to share and pick up, you know, so much new information or different methodology. And in some designs, that might be exactly what you're looking for. And, you know, it could save you quite a bit of time.
So active BOM. You know, I think we all know the value of using active BOM to look at availability and component life cycle. But one of the other things that I really like active BOM for is the group by function. And what the group by function allows me to do is search for redundancies in my design. And so, again, I've worked on projects where this is one of the last things that we do in the design process, where we say, okay, we have to optimize cost, and so we're gonna, you know, go through the design and try and eliminate as many unique SKUs for parts as possible. And by doing this group by function, I can sort, you know, by package and by value, and I can see if I have any redundancies. And I can make that choice. You know, like here, what I'm showing is I have a 0201 and an 0402 18 puff capacitor in my design. Well, that doesn't make a lot of sense. So I can eliminate one of those, consolidate to one package. And I don't know about you guys, but I've gotten a lot of heartburn over the past couple of years about sourcing capacitors. So I think this is a huge advantage.
Oh, definitely. Yeah, let's move on.
Yeah. All right, so we're into pre-layout simulation, and I'm going to talk about a couple of tools that I use for pre-layout simulation. Or some of the methods that I do. So one of the things that I do previous to any layout is I do a pre-layout simulation of my critical buses. And what I'm looking for in that simulation is I'm taking, the most important thing in here is the rise time, but you know, interrelated to the frequency. But taking the rise time, I'm doing a pre-layout simulation. I'm using a tool to look at the amount of crosstalk I have. And I set my crosstalk thresholds for specific buses or my noise margin. I look at my topology. But what I'm doing in this pre-layout simulation is I'm saying that if I locate two traces this close to each other, and what's the other critical parameter in this? How close they are and what? And Rick, you can't answer this question. Huh?
Close to the reference point?
Nope.
No, so there's the proximity of the traces, but there's another factor that's hugely important.
Thank you.
Couple length. There you go.
So yeah, the distance that they're parallel to each other makes a huge difference.
Yeah, yeah. And so I'm guessing a little bit, but you know, usually I'm going to overestimate on this and say, you know what, this part and this part are going to be about 5 inches apart. Worst case is I'm going to have a coupled length of 5 inches. And so then I look at, you know, using a pre-layout simulation tool, I look at the amount of crosstalk I have. And then I set my clearances appropriately. I'm not using rules of thumb for this. I am using a very rigorous process to do this. And then what this allows is a educated way to set up our design rules that's based in fact and not guesses.
Yeah, this allows you to not, over constrain or under constrain it. Like it allows you to, put the rule in that's the exactly correct constraint.
Can I ask a question?
Yes.
I know the answer to this, but I want to know.
I'm really nervous right now.
Tell people why crosstalk specific.
Well, I'm looking at I mean, there are a lot of factors that come into my signal integrity, but I am looking at crosstalk specifically because that is one of the things that I can control in my layout.
It's also one of the largest noise drivers.
Yes. Yeah.
And that's why it's important to look at crosstalk, among other things, but it's crosstalk specific.
Yeah.
So are you estimating how long the signals are? You haven't no layout yet.
I have not done layout.
Yeah, he mentioned he was guessing. So he's going to place the memory close to the processor.
Yeah.
And he's, and we know that it has to, take a C-shaped, route to get there. We know that there's, going to be a data and address bus, and we know that, one of them has to wrap around and one of them is going to be more direct. So he's guessing that, somewhat conservatively at 5 inches,
Yeah. So if I get to this point and I can't live with the clearances that, come out of this, I mean, if I'm getting, I so far in my career, I haven't gotten into a point where I'm making this fine of adjustments, but I mean, here I can reduce the coupled length, I can increase the spacing, and if my overly, if I think it's going to be 5 inches and it ends up being like 3, well, then I have to do an iterative process for this. Then I have to send this to do the layout on it, and then once I have the layout, I take the actual physical design and simulate that in this tool. Here's another thing, and we did this recently. This is a great company. It's called DFR. They were bought by ANSYS. But we did simulated drop testing. And we did a bunch of other stuff with them, but this is the one I want to focus on now. If you're building a high technology circuit board and you need to drop test it in the enclosure, you're not going to do that with 3D printed, if let's say in this case you're using plastic. You're not going to do that with 3D printed parts. You're going to want to use at least aluminum tools. So, to get to the point where I can actually drop test something is really expensive and takes a long time. And so what this allows me is to look at, the stress and the strain that are placed on my electronics by a drop test using 900 Gs, which is, I think that's equivalent to 31 inches. 900 Gs. Okay? I've worked on products that had to withstand a 200-foot drop, and that was 2,000 Gs.
So, one of the things that gets overlooked is it's not just the end use of the product, it's also the shipping that gets the product there. So that oftentimes will result in the highest stress that component is going to see. So if you ship by rail, when those rail cars are, going, one rail car slams the next and it slams the next, and there's high G forces when that car gets, pulled by the previous car. These are things that you should consider when you're, evaluating what kind of forces you need to be able to withstand.
So one of the ways that we're going to deal with, and we'll talk about this, but one of the ways that we're going to deal with stresses from dropping is your mounting hole placement. And what you need to do is be strategic about how you're placing your mounting holes. The other thing that is available to us, and one of the weak points of any design in my experience has been BGAs. And for BGAs, what's available to you is edge staking or underfill. But you can see how much that board twists in under a drop event. Yes. Sorry, microstrain, yes. Well, so this is the company that we had do it. They were bought by Ansys. They do a lot of great simulation and reliability. We sent our files to them. It saved us at least 1 or 2 design cycles. Yes. Well, it's hard to say if it matched, but yes, yep. So next we're going to talk about important decisions and discussions that need to be made ideally in the beginning of the project, but very soon. And you know, we heard this over and over again, and I think we're beating the same drum that a lot of people are beating, but don't make these decisions at the end of a design.
So when it comes to component placement, we have 2 options primarily. We put parts on one side or we put them on both, and there's advantages and disadvantages of each. So if we have a single-sided placement, then that's typically going to be lower cost because it's one operation in assembly. It's typically going to be a faster turn to assemble it. You're done after one. You're typically going to have higher yield because you're not thermally stressing parts a couple of times. There's fewer thermal excursions. The bottom layers can be a high-speed pair with no via stubs. If you're, you might have you're going to have a lower overall component density compared to the disadvantage is it is a lower density for the whole, for a similar size. You can fit more parts in a smaller board, if you use both sides. The decoupling capacitor placement, if you have a BGA or something like that where you want the capacitance close to the pin, it's much harder to do with a single-sided placement. So your component decisions for type of parts impact the placement of components into the board. So this is a decision that's driven by the schematic. If we have a BGA, we're typically going to have parts on both sides because we want that capacitance next to the pins. But not always, if it's a small part or if it's somewhat tolerant. The double-sided high density, we get a higher density with parts on both sides, and we can typically place things, closer together that way. And then, our connectors can be placed on both sides. But that, again, if you have through-hole connectors on both sides, now you're going to, 4 operations in this for, thermal, because it's typically a different process for through-hole parts as it is for surface mount parts. And then we typically have to allow room for a fixture on the bottom of the board, maybe 5 millimeters or 3 millimeters. With a custom fixture, so we have to be aware that, on the top we can put parts right next to a connector, but on the bottom, those through-hole pins typically have to have like a 5 millimeter clearance, or if we, pay more for the fixture, they can machine tool it and get a 3 millimeter clearance. So we would typically be, looking at a more dense placement, with a double-sided board, and then for assembly. And then, that's typically going to be a higher cost for the assembly because it's going to be on both sides. It's 2 or more turns. It's going to take a little bit longer to process that. And, there's more thermal stress on the parts. And, there's good advantages and disadvantages to both. If you're able to do it, all parts on one side, that's generally a lower cost, more efficient solution. But your parts and what's on your board are going to really dictate that.
And I threw one in here, and I just want to see if people understand this, but this one right here. And what I mean is if you've got, now you could do this with, components on both sides of the board, but this is a little bit of a trick in your stack up. If you want a high-speed signal without a stub, you can bring it out to one of your external layers. Now you have to couple those reference planes together that are, because you're going to have a reference plane transition when you do that. But, essentially what I can do is I can go from one to my bottom layer and get a via without a stub for that high-speed signal.
And having that side of the board free of components allows you to route them in a way that's going to let you route that.
And I want to mention this too. I mean, as a little, I think this is maybe not readily known, but laser drilled microvias from your outer layers to your first inner layer are generally a very low cost adder to your design. And they give you a ton of flexibility in what you can do. I'm not talking about an additional lamination cycle, but if your spacing in your stack up allows you to get an aspect ratio of less than 1 for that laser drilled microvia going from your inner layer to your next layer, it's a very low cost adder. And yeah.
So, your components that are on your schematic are going to drive your assembly costs. We have a high pin count BGA. It's going to drive the layer count up typically. It's going to it's going to force us to use more layers often. Not always, but usually, a high pin count BGA, is going to drive that layer count up because we have to escape out of it. And there's, the outer 2 rows we can get, but then we have to get the next 2 rows, and the next 2, and the next 2, and we just keep adding layers.
Yeah, and I'd say especially if that BGA is 0.5 millimeters, you have to have a serious discussion about the cost associated with adding that part. And just because it might be half the size of the equivalent part in a higher pitch BGA, it is going to cost you a lot more money and potentially take up,
sometimes the lowest cost component isn't the right answer because it forces you to a higher cost board technology. Yeah. And that's every engineer should be doing that equation when they, put a part like that on their schematic. They should know the ramifications of the PCB cost down the road.
I think another thing is, at the other end of the spectrum is through-hole parts. So, every additional operation in assembly is going to cost you money, and through-hole parts might seem pretty benign in terms of technology, but they can be a huge cost adder to your assembly process.
Yeah, if you can go all through-hole, all surface mount and not have any through-holes, that's going to save a whole, soldering operation.
Yeah, because generally, that kind of leads into this. If I have all surface mount, I can stay with this, my reflow oven during assembly. But if I have through-hole parts, I'm either having to utilize wave soldering or selective soldering. So Altium gives us a lot of great tools for defining board shape. I'd love to spend a significant amount of time right now talking about the MCAD collaboration tools. I'll just say they're awesome. But you have to define your board shape early on, and one of I came from startups and I went to a big company. One of the other things that was new to me was when I had an industrial designer tell me what my board shape was going to be. That was a hard pill to swallow, but I think at some point we're all going to be in that where we don't get to pick the board shape. It's dictated to us and dictated to us by someone who has no clue how to design a piece of electronics. Now there's some,
On the same token, if I may, the mechanical guys have to be somewhat flexible
yeah,
in working with the electrical people.
yeah,
Very quick example, the last board I worked on at L3, 3x4-inch board, with two 1,300 BGAs that had to be in the middle of the board, and the mechanical guy wanted to put a screw in the middle.
yes,
And I made it very clear to him there wasn't going to be a screw in the middle of the board.
Yep.
He eventually shut up.
yes.
Yeah, well, definitely making it work is the most important thing. And, you know, engineering is a bunch of balances. You are trying to balance out a lot of different considerations. And, yeah, I would guess everybody in this room that's a printed circuit board designer loves the fact that we get to make those decisions. It's fun. But it's super critical to understand what the ramifications are. So, you know, when you have a complex board outline like this, it's typically best to bring that in a DXF file. You can also get it from a step file and then create your board file from that. But typically, a DXF file is going to be easiest to import and get your board outline from. Sometimes you might already have a template that has that. But it's very helpful to have that. And then also, if the mechanical designer is giving you a board outline, you want to have where connectors are located and connector orientation and connector side. And if there are parts on both sides, they should be giving you both sides. You should be getting 2 DXF files so that you know exactly where things are supposed to be, because that mechanical engineer has planned all his harnesses and other connections to the board, and you have to get that right. There's nothing more frustrating to a project manager than learning that some parts were swizzled and they don't match up. You know, they're in the right place, but they're the wrong connection. Nobody's going to like that. So as board designers, we should be checking that and confirming with our mechanical team and our electrical engineering team, you know, on each design, just to make sure that that's right. And oftentimes things will get changed midstream, and, you know, just beware of the landmines that come with that. You know, make sure that everything's going to match up, you know, for what your pinouts are. Huge mistake, and, you know, it's a real big gotcha because it's going to come at the end when you find it usually.
So one thing I would say is, I mean, also in this, you should be deciding exactly where your connectors are going. And here's a quick tip I'll give you. If your design has connectors coming off of more than one side of the board, I want you to really pause and think about that. Because what happens when we have, now, you know, if you've got one that's a debug or intermittent connection, you shouldn't have to worry as much.
Or a connector to a backplane.
Yeah. But what happens when I have connectors coming off of 2 sides of my boards, now I've got a dipole antenna. And now I'm going to be wrestling a lot more with EMI. I've dealt with it, and if at all possible, have all of your connectors come off of one side of the board.
Yeah, the inductive loop's going to be much shorter that way. If they're on the same edge of the board, it's going to be a fraction of what the inductive loop would be if they're across the board.
Mounting strategy. So I think we could teach this is something that's kind of overlooked and something I've kind of learned on the fly about in my job. But there are, obviously screws. I mean, that's pretty straightforward. Another common mounting strategy is heat staking, which is challenging to say the least.
Yeah, you also have PEMs. You also have solderable screw connections, where you solder a part on and then you can screw into that. If you're going to have like a daughter board on a motherboard, you might have something like that. There's also, connectors that would be on a board where there might be, the most common ones like a DIMM connector, where we, put memory into a motherboard or something like that. There's also, clamping a board, where it snaps into place. There's, you can trap the board. There's card channels. There's edge connectors. you have a variety of different methods of being able to secure that board. So oftentimes that's going to really help you package a product better. There's also pin staking, where you might have a pin protrude through the board, and you've got a surface mount connection that's going to tie into that stake. So there's a lot of really creative hardware out there now. Just be aware of that.
But I have a strategy for it too, and this is where you need to bring in your mechanical engineers, and where you need to talk about the serviceability. So how is this thing going to be serviced? You need to talk about the types of vibrations that it's going to see. Another really important thing to consider in how you mount a circuit board is so if you're mounting this in a metal enclosure, are you grounding every single one of those mounting holes? Are you doing a hybrid connection where you're having capacitive coupling through some of those mounting hole connections and one ground connection adjacent to your primary power entry? You need to have those things figured out before you start laying out a printed circuit board.
Yeah. So also, like, are you going to plan on having a perimeter of ground vias around the board? These are EMI considerations that should be dealt with at this stage. You should know when you start the design, do I need to have a ground ring around the outside of the board? Are there any, we're going to get to shielding next, I think, right? No, okay.
Oh, well, PCB test strategy, and we need to start picking up a little bit of the pace.
Okay.
So PCB test strategy, if you don't have a good one, this is most likely the machine that you're going to end up on, which is a flying probe. It's expensive, it's less reliable, and it takes a long time. Okay, so don't put off making a decision. What you need to be doing is in a high volume application, which is what we're looking at in this talk right here, you need to be designing something so you can use a bed of nails. And when you're using a bed of nails, ideally you want your test points on all one side of the board. Now they can make beds of nails that come down on both sides of the board. Again, way more expensive, less reliable, wears out quicker, needs more servicing. RF. And I think I could teach a whole course on this here, but think about, in your test strategy, not only how are you getting to certain nets, but how are you testing your RF? Okay, so a lot of times you are not doing this it's been my experience, you are not doing this when the final product is designed. So you need to figure out how to test that circuit board and test the RF links on that circuit board prior to final assembly. Because if you wait until final assembly, then you're throwing out everything when that RF radio does not work as intended. We have used the light point tester from Light Point, and we have made provisions to do the programming of the PCB and the RF testing in one step in a RF box.
So this is important design considerations. When you're designing your printed circuit board for test, the number one cost adder is going to be doing a clamshell like shown here. If you can probe one side, that's going to be much lower cost. That's about 30 to 40% less. The other thing that's a big cost driver is the size of the pins that you're using. So in affordability, if you're trying to use a 15 or 20 mil pad, that's going to be a lot more than using a 25 or a 1 millimeter pad. So 1 millimeter might seem like it's really big, but it will save money, and those probes are going to be a lot more robust. And in high volume manufacturing, they will need to replace that expensive part. These fixtures might cost anywhere from $5,000 to $30,000, maybe $40,000, depending on how large the board is and how many connections. So, and they might need multiples. So by giving a good pin-to-pin spacing, you'll save quite a bit of money. typically I like to keep things like, I'll go with a 25 mil pad with, a 0.5, like a 50 mil pad to pad pitch. That would be a pretty standard test, configuration, because you can get them in, but they don't, necessarily drive your design so hard that it's, really difficult to get those in. Yes. Yeah, absolutely. So when you use a via, you want to make sure that that via is not tented or encroached. But
make it larger on the test side.
yeah, so if you want to save a little bit of room, you can, build a custom pad stack that might have like 25 on the top, and then, it might be like a 20 or a 16 on the bottom, depending on the hole size. No, they have like a diamond shape that comes down and probes, and if it's, if it's a little bit off, it's still going to contact that. It doesn't damage the via. It's going to have like 4 sides to it, so it's only minimally touching that via. It's going to touch like different quadrants of it, and they control the force that's on that as well, so that it doesn't, cause any failures like that. It's not crushing the board. It's not deforming it. Typically not.
No, you don't want to do something
because
with
those are going to vary a lot.
Yeah.
And that could be quite costly. We generally don't do that unless it's some weird thing that can't be tested any other way. We generally try to shy away from that because that's going to involve cantilevers and much more expensive mechanical fixturing. When they do these pins, they just want to drill it, insert a pin, put a wire in, put the wire to the computer.
You can even open up the solder mask on wide traces with broken traces, right?
Yeah, that can be done, or you can put a bead of paste down as well. That's another very fine pitch type of test method.
IPC's got a great table though, and what they basically show is for a surface mount test pad, that the minimum size before you start seeing serious fall off in reliability is 0.8 millimeter, but generally you want to have your test pads be, I think 1 millimeter is a good minimum size for a test pad, and it's easy to remember. Antenna tuning provision. So how many people in here have done antenna tuning? Okay. So a lot of times what you see is no one thinks about this, and antenna tuning is not solving a bunch of equations. Okay, that's how you get your start. That's how you get in the ballpark of how your antenna needs to be tuned. But after you tune your antenna, what you should be doing is an antenna characterization in an anechoic chamber. And no one thinks about this, and too often what people do is now the people characterizing the antenna have to remove the RF module, and then they have to put a coax onto the antenna feed, and then they have to scrape a ground plane, and you see these just Frankenstein setups with a coax and a bunch of solder. Put a U.FL connector in between your radio with some 0 ohm resistors like this that allow it to be removed and inserted without creating a stub. And you do this, and characterizing your antenna will be incredibly easier. And I don't care, so we tune our antenna for the input impedance into our antenna, the output impedance of our transceiver. And then we take this thing and we put it into a case, and everything about that case changes the antenna. And even, I want to emphasize this again, this was a learning for me, even RF transparent materials. So plastics change, not by a ton, but they change the characteristics of your antenna, and your antenna needs to be tuned after it's put into the case.
They have a dielectric constant difference in air,
Therefore, exactly.
Absolutely.
Thermal strategy. So, sometimes we can't think about this until we're at the very end, but you need to have a conversation about it early in the design process. How are you getting heat out of your design? And I think, obviously the two ways that we can do that is with active cooling or passive cooling. Now, passive cooling can include everything from heat stakes to thermoclad substrates, but it's something that you need to think about, and I would advocate that you don't put it off till the very end of the design and you start having some initial conversations about it. I would imagine that you have some pretty
it's
thermally interesting boards.
Oh, absolutely. So, it's very important to know what your options are in this area. Typically if you're going to be doing active cooling, you'll have a fixture and it's going to have, areas that come up and there'll be, fluid passing through that, which will be connected to a radiator somewhere else. And what you want to do is, have those parts contact that. So it means that the hot parts are going to be, on the bottom side of the board, and then the top side of the board, would be reserved for other types of parts. But it's super critical to, look at the thermal management of your product. Obviously, active cooling is way more expensive, but it also allows you to, mitigate thermal issues much better. So even though it's more costly, it's very cost effective, and it often will result in a much more dense package overall. So you'll be able to design an active cooling product in a much more dense space than you would a passive cooling product, typically.
One tip that I would give at this point is just because you don't have a fan on your device pushing air through it does not mean that you're not going to have airflow. And so one of the other things you have to think about, even if you're using passive cooling, is line things up with your heat sinks so that they permit airflow. Don't just do something haphazardly, because as soon as heat starts getting generated in your electronic device, it's going to start creating convection, airflows within it, and things should be set up in a way that capitalizes on that.
Yeah, so it's really important to know the final product mounting. Like, what's the orient? Is my board flat? Is it vertical? Is it vertical this way? It's really important to know that so that you can arrange the parts so that when the thermal comes off a very hot part, it doesn't have another part baking in that same stream. We want to spread parts away when we do our placement so that we can mitigate that heat, especially if we're doing passive cooling. I don't think it makes a difference. I generally see air pulled, but you're going to have airflow, and sometimes you'll see both, where you push it and pull it. But that's going to be, like the thermal modeling team is going to be able to look at that and tell you exactly, how many cubic feet per minute they need. Like, they're going to tell you the volume of air that's going to be exchanging. And then what also matters is like what your end environment is. Is this thing going to be inside a room like today, where it's fairly comfortable, or is this thing going to be in a hot desert? Is it going to be, is the end product going to be used in sub-zero temperatures? Like, we need to know where it's going to be used, how it's going to be used, what's the environment. Like, that's going to drive those thermal decisions. And there's very, very good modeling for these thermal issues now. The tools we have now for this are pretty amazing.
So what I would, and I hadn't thought about that, but I think what you're hitting at, Rick, is by pulling the air, I'm taking advantage of hot air rising, basically.
Right, and you're pulling, yes, and if you're pushing, there's the risk of disturbances causing freezing.
Yeah.
That's my thought. I'm not much of an air expert.
Understanding the bigger picture is always best.
Absolutely.
So shielding, this is, again, another thing that you need to have a discussion about early in the design. And not doing this just to solve a problem at the end, and having a discussion about whether you're going to include shielding or not.
So the cost of shields is generally going to be determined by the complexity of the operations and the cost of the tooling. So here in the lower part, you see like a steak that has a cover. The top one looks to me like it's a single shell that's been manufactured, from a stamping. So the cost of the shields is going to be greatly determined by that. The nice thing about a cover is you can pull it off for your testing and put it back on. The difficulty, if you can keep a square rectangular shape, that's going to be much more cost efficient than an odd shape. And you probably can get, parts off the shelf from the manufacturer of these. But if you're doing any kind of volume at all, they usually will do a custom setup for you.
One thing I'd say about shielding is you don't use a shield by just slapping it down on a circuit board. Okay, if you put a shield onto a circuit board, you need to think about filtering all the signals that come out in and out of that shield and how you are protecting those signals with filters. Because if you just throw a shield down on a circuit board and don't think about that stuff, it's coming in anyways. And so now you've just bought a really expensive decoration for your printed circuit board. You got anything to say about that, Rick, or does that?
I actually have a lot to say, but I won't.
Okay. ESD. So
Boom.
Protecting against ESD is not putting a TVS at your connector. The way that ESD, is such an extreme event, is the pathway that ESD takes is to capacitively couple with the earth. So that is the most likely, especially on a portable electronics. Otherwise, if you have a safety ground available to you, you want to be dumping your ESD currents into that safety ground. But on a portable device, putting an ESD diode on an exposed pin does not protect you. Okay, you need to think about where that current is going, and on a portable device, like I said, it's going to capacitively couple back to the ground, so you need to think about that. Most likely what that means, most likely what that means is there is some larger plate in a lot of like the TI calculators, they put in a plate, and the reason that plate is in there is to form a capacitive coupling with the ground. And that's where you dump your ESD. So you need to have a conversation about this. The other great way to protect against ESD is don't expose electrical contacts to the outside in a way that can be touched by a person. You're still going to have to do the air discharge, but air discharge is easier to protect against than the direct contact discharge. And so just, you'll see on your phone, there are no exposed electrical contacts. Your USB connector is recessed. And that is how phones mainly deal with ESD events. Okay. We got to start cooking.
Okay.
I wouldn't say like turbo, but
Okay.
definitely.
So when you bring your parts in, they come in like this. They're in different rooms. They're scattered. This is very helpful for us. We have all these different rooms, and there's a couple ways to strategize your placement. This is how we start when we load it in from the schematic. So based on the board density, let's go to the next slide right now. So this is all the parts loaded, and we've basically just put them in, and we can measure how big this is, and we can look at that compared to our overall board real estate. If the board real estate is smaller than the component real estate, we have a problem. If it's 90%, we still have a problem. If it's in the 70 to 80%, we generally can design that. I've done designs that are component to component on the whole body, but very painful design, and it's a lot of work. If you're in the 50 to 60, maybe you're wasting room. But you can, judge very quickly, like, how hard is this design going to be? And then you know what your component density needs to look like in your different circuit blocks once you've done this study. If you know you're at 60% or 90%, you're going to be placing those components a lot differently. If it's 90%, you better not waste any room because you're going to run out. So let's go back to the previous slide. So now that we have these different rooms, what we want to do is locally place these so that each block is as efficient as possible for that functional block. And by doing that, now you've essentially created the puzzle pieces that are going to fit into your board. So I've seen a lot of different methodologies. I generally will follow that in about 90–95% of the designs I do. If it's a super high density board, you might find that it's easier to start on an edge with a connector and pack everything as densely as possible. Don't forget about your test points. And just smash things together as closely as possible. Do whatever routing is necessary to find out what the component spacing should be. Make sure you have escape vias. Make sure that you have BGA. Make sure that you have test points. For a high density board. But I would like to do all of that pre-placement in local groups before I bring everything onto the board. So let's go. Let's go to the next one. So when you do your placement, we want to place things in a way that is going to facilitate the routing. Good placement makes the routing easy. Horrible placement, especially if it was somebody else's and you inherit it, will make you pull your hair out. Looking at your net list and minimizing the amount of routing based on your placement is the most valuable thing you can do in the PCB design cycle because it's going to minimize the overall length of all the traces. Noises, there's going to be, it's very important to put things that are high speed. We want to, what's the order in which we look at these different, at placement? Connectors first, anything that's fixed is first. Anything that's, a mechanical issue that has to be in a particular place, switches, LEDs, anything like that that's part of the function of the product, also has to go in first. And then we look at what's left and we look at how we can arrange this. Now, it's very important to also think at this time, where am I going to route the bus between these things? Do I have room for that to run? And am I trying to do that on a part that's going to, be perforated with vias and block that? Or is it, so that's really important, when we look at the routing. Routing channel should be a part of your placement strategy.
So I'll just say real quickly, it was interesting to hear that Carl and I had a very similar approach to that, and that we do the functional blocks and we do that first, and then I put the puzzle pieces together on the printed circuit board. But one of the things that I try to do, after I've placed those puzzle pieces together, is then I try and organize things in kind of a systematic way. So I have banks of capacitors or resistors, as long as they're staying in the optimum position. I'm not doing, some crazy scattering of parts on my circuit board.
Yeah, one more thing on that. It's easier to modify a placement that's been done in a minimal space than it is to try to fit that into an area that's not conducive to that part. You might do a little bit of modification, but you're almost always better off doing a pre-placement. It gives you a really good idea of how much room you need for that circuit.
So setting up differential pairs, like setting up rules, this is one of the things that I'm doing in the beginning of, prior to laying out any trace in Altium, and Altium has introduced a lot of tools that enable us to do this easier with the impedance profiles and the stack up. But this is definitely something that I do at the beginning with my differential pairs and setting up my rules associated with those. And this, what I do when setting this up is, and I could spend, and well, you did give a presentation on stack up last year, but one of the things that I think is really important is having a very robust conversation with your manufacturer. I mean, your stack up isn't just how your layers are arranged. It's not just how your signal layers are adjacent to ground layers, how hopefully your power layers are adjacent to ground layers, but it's also talking with your manufacturing about reliability, talking about CAF, talking about your via structure, talking about how the decisions you are going to make affect the reliability, the manufacturability, the cost, and the time it takes to manufacture your circuit board. And I think with stack ups, it's been, I start from a ideal. A lot of the principles that I've heard, Rick talk about extensively at this conferences, and Carl, and I start from that ideal. I've always found that I can never make the perfect stack up. There are always, some trade-offs that need to be made, but you need to understand what those trade-offs mean and how you are not going to let those trade-offs bite you.
Yeah, I would agree with all that. The stack up is going to be the #1 cost driver of your board after the size of the board. And it's also going to be probably the #1 determiner of the reliability of that printed circuit board as well. And yeah, absolutely. If you're able to, arrange your stack up in a way that all your signal layers have a reference ground next to them, that's as solid as it gets. And if you have a high risk design where there's, a lot of interconnects, why take a chance of having crosstalk? Just put a ground plane in between it. Like there's just, if it's higher risk to, have signal integrity problems than it is to, add a couple layers to your stack up.
One of the places where I find myself making trade-offs, and I'm looking for Rick approval on this, but asymmetric strip line is not ideal. It's not ideal, but here's what I can. You sometimes, and more often, I get stuck with it more often than I'd like. But one of the things that you can do to minimize the effects of asymmetric strip line, and just real quickly, asymmetric strip line is ground, signal, signal, ground. Okay, what I can do to minimize the bad effects of that is I can route the traces on my 2 layers perpendicular to each other. And that actually makes the layout easier. So if I stick to that rule and say traces on this layer are only going horizontal and traces on this layer are only going vertical, and anytime I want to go vertical, I'm transitioning from the horizontal layer to the vertical, all of a sudden at the end I've fit in way more stuff because all my traces on one layer only go one direction, and it makes things so much easier.
You can definitely get a lot higher density if you bias your layers, opposite each other. Cost. Yeah. They want to make money.
If the automotive world had their way, every unit would have 0 weight and 0 cost.
But I will tell you that one of the hardest stack ups, I won't use a 2-layer board for a high-speed design. And I think this is a true statement. Well, this is a true statement. The second part I think is a true statement. One of the hardest stack ups for me is a 4-layer board. You can't get around it. There's no ideal way to do a 4-layer board. The Xbox is a 4-layer board, right?
Right.
Look at what is on an Xbox. There's every high-speed interface. So, we want to obey design rules, but they got it done. And so, but I know they put a lot of engineering into that.
They did, but they also didn't put power and ground on 2 and 3.
Yeah.
They distributed power with signals, and believe me, they put a lot of time into this. I actually had some involvement.
Yeah. That is an amazing board to me.
Controlling your reference planes is extremely important. I'm super glad to see that come into version 20 of the Altium tools. I think that's going to help all of us be better board designers and to be able to look and find those kinds of errors, because they make a really big difference, especially as the speed of our edge rates increases.
Stack up. So, again, Altium has really come a long way in the stack up manager and creating impedance profiles. I will say that last time I tried this, I had to manually input my impedances for asymmetric strip line. It did not like referencing a ground plane that was more than one layer away. And I think that's still a true statement, but I could be wrong on that.
So since you mentioned that, I want to mention one thing, that if you're designing an antenna and you want it to be more accurate, you want to do exactly what he says. Instead of referencing, like if your antenna is running on layer 1, don't reference it to layer 2, cut out layer 2 and reference it to layer 4. Now that can be twice as large, and the accuracy of that antenna is going to be much better.
With an antenna, don't you want it to have no reference in the board?
Well, the antenna itself, I think you're talking about the feed line.
The feed line, yeah.
Yeah.
Mm-hmm.
Yeah.
Yeah, from your part to the antenna connector. Yeah, you can have a wider trace if you reference to a layer that's farther away. And the tolerance of manufacturing now is going to be a far less, it's going to be a much more accurate trace by doing that. Everybody should know that that's an option. If you're working with an engineer and he's not aware of that, you might want to suggest that to him.
So visualization of the stack up, just a very cool feature in Altium. Setting up X signals, and if we got time, although I think we're going to be hard pressed for time, we were going to show a demo of setting up X signals within Altium Designer, but this kind of goes on to the setting up rules, setting up differential pairs, and setting up my X signals.
So we bring in the classes from the schematic, net classes, PCB classes. If you have, you're going to create pad classes in your board, usually a non-plated hole needs to have 0.3 millimeters away from copper. Those are the kind of rules that are set up in the PCB after the schematic comes in. Binary, the binary type rules where it's something to something else. The class rules would be set up there. And then, there's really, really good information on Altium's website about how to do all that stuff. I don't think we need to cover that.
And one quick thing I'll say is one of the additional classes that I use quite frequently is pad classes. And I will use that for breaking my thermal relieving rule. So if I'm doing a polygon pour on a switching node of a switching power supply, and it's a polygon pour that's relatively small, and I don't want it broken up by thermally relieving, I will create a pad class for all of those pads, and then create a direct connect for that polygon on that switching node. So setting up rules and constraints. Let's just say that Derek, I heard your presentation, which I had to skip because I was still putting together slides, was amazing. And so I think, and that was coming directly from Carl. So if you didn't get a chance to
I do say it was an amazing presentation, and you're going to want to check it out.
Yeah. So a guy, how long, you said you've been using Altium how many years?
Since 1985.
Okay.
I was user 600 something
of
the tool.
If he says that he learned a lot from the rules presentation, I think we should all watch the rules presentation. Because I will say that someplace I still get very confused is setting up rules in Altium Designer. I hate to say it.
Yeah, if you run rules, usually it's going to color code rules that have errors.
Yeah.
Differential pairs will often, if you have the same exact value, if you're working in metric, oftentimes it'll flag those rules as not right, and you'll have to go back and put a minimum and a max value that's maybe one tick of your measurement system away from what the preferred rule width is in order to get those to clear?
So, sometimes queries, for the life of me, do not work the way I expect them to work. One tool that's really helpful for me is I can select something by using the find similar, and then I set up all the things that I want to find, and then there's a checkbox at the bottom that says create expression. So I've used that numerous times to cheat on, instead, and then cut and paste my rule.
Yeah, you can use that to start your rule. Really, really good technique because you can see what the rule is going to apply to, and then write your rule with that condition.
Yeah.
There's actually a button to write into your rules. It's
Yeah.
green on the roll.
Oh, really? Okay. All right. Yeah. Yeah. Yes. 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 I have found, though, that I've built a query doing this exact method and then thrown it into a rule and it doesn't work. So I don't want to get into the details of, well, yes, but yeah.
Yeah, sometimes it's pretty challenging to sleuth the rules out, and that's when you might call tech support.
All right, we're going to do a quick demo.
Am I on here? Audio? Good deal. What I'm going to do is just go ahead and, at this point, just hit some highlights of some capabilities that are in alignment with what Max and Carl were talking. Let's go ahead and first look at the harnesses. It's a really key capability. It's really cool. I'm one of those that also hasn't really used that too much. Let me go ahead and just give this a shot here of highlighting this area. Need to check my, yes. Let's go ahead and choose everything here. Highlight this area. And then I can do a Control C. Then if I've done this right, I can come in here to Smart Paste. And I can choose the harness connector and port. And we see we get this. And what's cool about that is the system remembers that. If you have existing legacy designs and you want to move it over to the port methodology, if you will, it makes it very easy to do. Now I'm going to be switching into some other design files here. I've got a scenario here. This really is a top level diagram. We've got our table of contents. It's an entire mini PC, and we've got this block down here. We can go inside of here, easy, and check that out. Actually, it's open right here. And the thing that I'm trying to mention is that if I wanted to place a harness, I can choose predefined harnesses. Now, there are multiple places where you get predefined harnesses. You can either create them. It might be a proprietary bus or something you have on your boards, but it also remembers anything that you put in there. So I'm looking for my JTAG interface. It's right here. I can see my members, and then I can just go ahead and put that in here. Okay, and I've got my auto compiler set. I don't know if you guys have seen the situation with auto compile, but that's part of our new dynamic data model. We're going to probably be in about 5 minutes or so going to a final phase of Q&A. Go ahead and clean this up a little bit here. So what I'm going to do is move my signals around. Let me first make this. I'm having a hard time. There we go. I'm going to go ahead and move my signals around here because this is the way it comes in. Let me go here. Let's see, TD. Just showing you in the real world how we'd have to do some of this. Okay. Okay. Okay, we go ahead and clear this up, and then we can, bless you, we can come over here and just connect this up. The key point being is that these harnesses, these are important tools for having what I would call reusability. You get a reuse bus, and like Max was saying, you can use just the net names to connect the remappable pins, and you have greater reuse and such. So the other aspect I want to cover, and I'll jump real quick into the presentation, just wanted to make sure, in case any of you weren't aware, what exactly is a class? We talk about these classes. It's a logical collection of a particular type of objects, nets, components, and more. A class can be a target for design rules. We talked about that. They can be auto-generated through the compile step. We talked about that. Max and Carl discussed that. It supports a higher level abstracted visualization in your PCB. Now, maybe I'm just alone in thinking that's cool, but it really is something that is very useful. And so I've got this mini PC here, and when we go to our PCB panel, I can bring down the various classes. Let me make sure that I'm in the, I want to make sure that I'm in the view options here so I can, yeah, that looks great. So we can start highlighting these, and this gives you another way to evaluate, do QA on your board. I know when I took some of my old designs and put classes on it, I was surprised it even worked. I'm surprised anything I've designed even works after the last few days, quite honestly. So these are net classes. We've got X signals that we've talked about. This is an important panel for looking at all of this information. These are all differential pairs. Component classes, very important to understand, like I believe we might have one here. Power capacitors. So you get a visual. A lot of times when you have bypass capacitors and such, they're just going to be in your schematic anywhere, but they need to be near the device. I think we are coming down to a 5-minute mark, and at this point, I know this was very quick. I just tried to go with some high-level stuff. Do we want to open it up for a Q&A for everybody here?
Okay, just a moment.
No problem.
You mentioned X signals, and one of the things we found ourselves doing is in large Xilinx parts is mapping the delay in the die itself over the total length matching for X signals. I was wondering, or I heard a rumor that you were going to address that in one of the next phases of the software. I wonder how far you got with that.
I know they've introduced the pin and pin package mapping. Yeah, pin package mapping.
Yeah, so it's currently not being added to the X signal because they have the pin package mapping, and it should, because I think if you go to the X signal, it has a column. I think it includes the pin package mapping. So so in here, if you go down to the bottom, then it should have the different columns. And it should have the signal length and the routed length. Because the X signals will calculate the signal length, which can be different from the the routed length. So in here, especially if it goes across multiple pads, and so what he's referring to, inside the chip itself can have extra routing, and you want to include that into the calculation. So should be a pin package link you add to the pad.
Total pin.
Yeah, and so it should be automatically calculated. You just add it to your pads, and then it should, when you generate the X signal, it should pick it up.
Derek, where did that information come from?
Excuse me, sir.
Data sheets.
Thank you.
Okay.
Oh, you have to download the file.
Question about you showed daughter board, motherboard, or pair of boards where you had the net names for pin swap on your schematic. Wouldn't that be best done in a multi-board?
That was a reference. I had to pull out one of Altium's old reference designs.
Okay.
So it was prior to multi-board, but what I just wanted to emphasize in there is not making that direct connection.
Okay.
Yeah.
Anyone else?
I'm not that familiar with how it's done in the industry. I worked in one company for my whole life. But I was wondering about using one tool for schematic capture and another tool for layout, and how often that's done. And obviously there's big disadvantages to doing that, but do you have any comments?
It's bad juju. I wouldn't try it. Like you can do it. You can actually read a net list in, but you're going to cry every day with that methodology. Like Altium gives you the schematic capture tool. It's like, Fisher cut bait and hand them a stick of dynamite. They're going fishing. Tell them, you're better, being in the Altium schematic and being able. The advantage of having the ECO generation tool is one of the biggest advantages of Altium Designer. To be able to, have the libraries organized the way we can organize them and be able to rapidly update your board without any trouble is pretty great.
And cross.
I get a lot of scenarios where people have a reference design, it's in one tool, like an ORCAD, and I know Altium does have some capability to convert like an ORCAD design to an Altium design. Does that work out pretty well, or no?
You can import Gerber shapes, into a design. They come in as entities, so there's definitely a lot of work to doing that. If you don't have to do it, it's easier, but sometimes if you get some weird shape that has to be duplicated, you can bring that in identically to how it was created.
Just to comment on reference designs, you should probably never use an IC company's reference design. They're terrible.
Yeah, I designed a RF board recently that did 100 dB better than the reference design.
Yeah, so you can always.
That's a lot. That's a huge amount. It's 40% better.
Yeah, and what I would say about the import process into Altium is it's a good starting point, and I'm not talking about the quality of the design you're importing, but I would say in my experience importing a design to Altium gets me about 50% of the way there, and then I still have to do.
Starting point. You just said it.
Yeah.